Hi, I'm Maddie, and this summer I worked through Cough Lab um, to look at assessing antimicrobial compounds produced by soil bacteria isolates. And we are doing this largely because of something that's going on called the antibiotic crisis, where the things that make us sick are building defenses or antimicrobial resistance versus the medications that we use to treat them, like penicillin, for example. Before penicillin was first released in the 1940s, infections were the leading cause of human death. And the situation we're looking at right now is bringing that back, what we're calling the post-antibiotic era, where we can start expecting thousands of deaths within the next 20 years or so annually in the US alone. And things like surgeries that are very commonplace, like tonsillectomies, could become too risky to perform, and common infections like an ingrown toenail could be deadly or truly debilitating. So we are looking at soil bacterium because a lot of the antimicrobials and antibiotics and medicines that we already use come from soil bacteria, but less than 1% of bacteria have been cultivated in a laboratory setting. So we expect that if we can find and isolate and examine more bacterial samples from the soil, we're likely to find new compounds that we haven't used before, which the things that make us sick don't have defenses against yet. It's a long process. When you isolate soil bacteria, you have to identify every organism in the bacteria. And then you have to take the ones that you haven't seen before and see if maybe they produce compounds. Maybe they produce compounds if you give them one food source versus another. Maybe they produce compounds when they're grown alongside other organisms or when they're alone. So you have to look at all of that. It takes a lot of time. And eventually, even if we find new organisms and new compounds, the things that make us sick will build up defenses against those too. But this can buy us time. And that time will allow other researchers, like some of what Dana's working on, to explore options that aren't antimicrobials for treating infections, such as quantum dot technology, or one of my favorite ones to look into is bacteriophages, which are viruses that only kill bacteria. So what I was doing this summer is I was taking bacterial isolates that were isolated by a previous class through Sebastian Koff's lab, and growing them on plates. I grew them on a Lauria broth medium, which is like a starchy carbohydrate food source with a lot of vitamins. And these are the plates that I cultivated them on. And then I put them through a DNA sequencing analysis because, again, we have to identify the bacteria that we're working with, see if we've seen it before, see if we see anything new, or if it's related to things that we know produce antimicrobial compounds. So I did something called a polymerase chain reaction, which essentially uses varying temperatures and a special enzyme mixture through a thermal cycler to replicate the genetic strands over and over and over again, more than 1 million times. And then I did something called gel electrophoresis, where we make, it's called a gel because it's got like the consistency of Jell-O. And you put your amplified DNA or RNA into these gel wells, and you send electric current through it. And if it's successful, then you start to see these glowing lines under UV light that tell you, yes, you have genetic material there. It is in a quantity that can be detected. And from there, after we've done the genetic sequencing, we then extract compounds produced by our bacteria. So we take a fully grown plate of bacteria. I had to grow new ones for this. We chop it up and we stick it in a vial. We fill that vial with methanol or ethyl acetate. I mostly used methanol. I did try an ethyl acetate run, and other solvents. And then we put it in a shaker for a while. That really helped that solvent mix into the plate. Then it separates, so all the goo and stuff from the plate goes to the bottom, and the extracted compounds with the solvent stay up top. We pull the top layer out of the bottle and we stick it in a smaller vial, which we then dehydrated under nitrogen. That's a nitrogen evaporator. We weighed our compound vial after dehydrating it to see how much material of extracted compounds there was. And then we rehydrated that extracted material to a certain concentration, and we put it on clean plates that we then inoculated with E. coli. E. coli is one of the things that makes us sick. We used a non-pathogenic E. coli in our lab, but it's still a close relative. And if there are antimicrobial compounds in that material, we should start to see a halo effect around where the compounds were dotted. Okay. So throughout my project, after a few dozen tries, honestly, I finally had successful PCRs and DNA sequencing. I referenced them against the National Library of Medicine's database. They have a huge database full of genomes and genetic codes, and I was able to identify 2 isolates that were likely to produce antimicrobial compounds. One of them is pictured here. Yeah. However, my antimicrobial extraction tests did not work. The E. coli still grew. I tried a handful of different methods to do this. I also did this with compounds extracted from organisms that we know produce antimicrobials, and those also did not work. So, let's see. In questioning why it might not have worked, this was our big process, and there's a few reasons it might not have worked. The food could have been the wrong food. Depending on what we or other organisms eat, we create different chemicals. The extraction process definitely needed adjusting. We tried a handful of different protocols, and so it's worth looking at more protocols and potentially more solvents. Maybe these things don't extract well in methanol, and we need to be using a different organic solvent. It's also possible that our antimicrobial plating process was an error. I couldn't find a distinct protocol for that, so we were kind of just developing them. But it's all worth looking into. The other thing worth considering is that I was growing these as isolates, so only one organism per plate. And when organisms produce antimicrobial compounds, they're doing that because of competition. They're trying to kill the other things that are fighting for resources in their environment. Growing them as isolates may have not prompted them to even produce the compounds because they didn't have competitors for their food source. So future research, which should have more time, can look at all of those things. There are a handful of isolates I ended up extracting with 2. There's 19. So hopefully future researchers can do more extraction protocol examination on these isolates or grow them on other forms of food. Yeah, and we need follow-up research. And if we do end up with positive results on our antimicrobial extractions, we'll then be wanting to test them against yeast. Yeast is a eukaryotic organism, so are we. If our extracted compounds kill E. coli and yeast, we probably can't use them as medicine. So yeah, this is references, and I'd like to thank all of our funding sources, wonderful people at RECCS, my mentors, and Professor Sebastian Koff, he goes by Seb, as well as our lab manager, Adam. He was a huge help. And Toby Halamka, who provided great support and guidance, and my partner, Wookie. Yeah.
Quick question for Maddie?
I just have a quick one. How long does all that take? Like, is it a week or a month? I mean, it seems like a pretty intensive
yeah, so each PCR took roughly 2 or 3 days. I got quicker at it longer in the program. The first couple times it took a very long time. The gel process is pretty quick. We needed to send it to an external lab to do the sequencing, so that took a day or so. And then the methanol and ethyl acetate extractions varied. We tried a handful of different protocols. One of them took 72 hours. One of them took 24. We did one for a 1-hour mixture. We tried many, many ways to make this work. It just really varies. So somewhere between 1 and 3 days per process. Culturing them took 1 to 3 days as well.
Does the methanol kill the bacteria?
Yeah. So I don't know if that's the intention, but it definitely kills the bacteria. One of our compound tests, we did a control where it was just methanol, and we were plating it on a grown plate of E. coli, and we discovered that yes, we got those antimicrobial regions, but we also got those antimicrobial regions when there were no metabolites. So the methanol was killing the E. coli, and we needed to reevaluate how we were plating it.